Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Happy to introduce Nirlo. He's working down in the Silicon Valley office right now. And normally he's at Princeton, where he works on a number of areas, including algorithms and testing. And today he's going to tell us about generalizations of the three-sum problem.
Okay, thank you very much for inviting me here. I'll talk about lower bounds for linear degeneracy testing, which is a problem that I think is very fundamental and interesting. And this is work I did with my advisor, Bernard Chazelle, a year and a half ago. And there are still some open problems that, some open questions that I hope to interest you with. So what is the r-linear-degeneracy testing problem? Abbreviated as rLDT. So the input is n real numbers, x1 through xn, or a point in high-dimensional Euclidean space. And we ask whether any r of them sum up to 0. Or in other words, is there a sequence of r indices I1 through IR such that the sum of the corresponding coordinates equals 0? Okay, it's a very simple question. And we assume here that the number are reals, and we're not asking questions about representing them in a computer or anything like that. So this is an algebraic model of computation. Okay, so why is this problem interesting at all? Does it have any motivation? So the answer is yes. So in computational geometry, many times we'd like to write a program that does some geometric computation, and then there are all these corner cases that we call not in general position, that we want to ignore, but somehow we cannot ignore because they happen in real life. So what does it mean to be in general position in r to the d? So every problem has its definition. It usually means that there is a family of polynomials that has 0 when you substitute the variables with some of the variables from the input. So for example, a Voronoi diagram is degenerate if too many points in the input lie on the same sphere. So in 3 dimensions, if 4 points lie on the same sphere, then we'll say that the input is degenerate. And this can be tested using some polynomial. It can be written quite easily. And there are problems which I call bichromatic problems. Say the input is a bunch of lines and points, and we want to know if any of the points lie in any of the lines. So this is, again, a property that can be expressed using some polynomial. And there are many more such problems. And the reason it's called, these properties are called degeneracy is because if you take some random input, then the degenerate instances will have 0. So they're very unlikely to occur, but still we're interested in them. For the case r equals 3, that is asking if in our input there are 3 numbers that sum up to 0. So this problem is also known as the three-sum problem. And Gajentan and Overmars in 95 define a class of three-sum hard problems. These are problems that are reducible to the three-sum, or to 3LDT. And the open problem in this field is whether whether there's a lower bound of n squared on the complexity of three-sum. And the best known lower bound is n log n. But the best known algorithm, the upper bound is n squared. So here's an example of a three-sum hard problem, just to show that these problems are not are quite interesting. So for example, given as input a bunch of triangles in the plane, we ask if they're simply connected, whether their union contains a hole. So in this case, they do contain a hole. Also, rLDT somehow captures NP completeness, because if you assume that the input is rational, and you assume that R is part of the input, then it's easy to show by reducing from subset sum, for example, that the problem is NP complete. It's NP complete. But we're not going to talk about the Turing machine model. We're going to talk about an algebraic computational model, which is more suitable for this problem, and it raises some interesting questions. So the computational model is called the linear decision tree. So what is a linear decision tree? So it's an algebraic circuit. It's a tree. It's a non-uniform computational model, meaning that we do not care about being able to compute the tree using a program in C for any input of size n. We're just asking, does there exist a tree of depth so and so of size n for input of size n? So the tree will be a ternary tree, although it can be also done with a binary tree, but we'll assume a ternary tree. And every internal node, asks a query. So what is a query? A query is a hyperplane in the n-dimensional Euclidean space. Okay, so it's a linear polynomial in n variables, t1 through tn. So every internal node in the tree has such a query attached to it, and the outgoing edges from each internal node are less than equal or greater than 0. So how do you compute using this tree? You take your input, you start at the root, you evaluate the polynomial, the linear polynomial at the root, and then you branch on whether the result is less than 0, equal to 0, or greater than 0. And you continue so on down the path of the tree until you reach a leaf. And a leaf is marked with either yes, meaning the input is degenerate, or no, meaning it's not degenerate. And the locus of points that reach the yes leaf is, by definition, the language that the tree accepts. Okay? And we say that the complexity of a language is the minimal depth, not the size, but the depth of the tree that decides that language. Okay, so we're allowing the tree to be exponential size, but we're asking about the depth of the tree. We want that to be small. So here's just a drawing to show what this computational model is all about. So say the input is in 50-dimensional space. So in the root, we ask whether x1 plus 10x3 minus 2.5x20 plus 5 is less than 0, equals 0, or greater than 0. And then we continue down the path until we reach the leaves, which are labeled either yes or no. So previous results. So Mayer-Aufderheide in '84 shows that the linear decision tree can solve the knapsack problem in depth n to the 4th log n. Okay, so this was a surprising result at the time. It was conjectured that it cannot be done in polynomial time. And in fact, his result also applies to our problem, rLDT. So the problem has a polynomial time solution, and the exponent does not, the degree of the polynomial does not depend on r. Okay. Meiser in '93 showed a similar result using different techniques, but he showed something more general, but it also applies to this problem. So namely, he showed that in polynomial time, you can solve the rLDT problem. But both these results are non-constructive. So the linear decision tree that can be used to solve rLDT according to these results is non-uniform, which is okay because that was part of the definition of the linear decision tree.
Is it a randomized construction though that works with high probability?
No, I think it's not. So Erickson considered this problem in the late 90s, and he has a great result. So let's see, first of all, what he assumed, and then we'll see why he assumed that. So first of all, he took the model of computation, the linear decision tree, and he further restricted it. So what is the restriction that he assumed? He added another parameter, s, to the computational model. And he says that the queries, the hyperplanes that the algorithm asks for can have at most s non-zero coefficients. Okay, so for example, if we say s equals 2, then the algorithm can ask, it cannot ask the first polynomial, the first hyperplane, because it touches three inputs, but it can ask the second one, because it only asks about x3 and x2. Okay, so only two non-zero coefficients. I'm not counting the -5 and -1. And Erickson showed that assuming this model of computation, where s equals r, that is, when you allow exactly r non-zero coefficients in each query, there is a lower bound of n to the half r ceiling for the depth of the linear decision tree deciding rLDT. Okay, now why is it natural to ask for s equals r? So if s is less than r, then it's very easy to show that you cannot solve rLDT. So a tree that has s less than r, that does not ask queries with at least r coefficients, cannot even decide rLDT. And it's very easy to see how to come up with an algorithm, a linear decision tree algorithm that decides with r coefficients. Just try all possible choices of r indices, right? But he showed that there is a lower bound of n to the half r, and in fact, so this problem is interesting because there is a uniform upper bound for this problem using the same restriction that Erickson assumed. So in fact, you can solve rLDT in depth n to the r over 2. Okay, and I'll show that in a second. It's a very simple result. And that's one reason why it's interesting. I think the other is it's a nice generalization of what we call the comparison model. So we all say that sorting is n log n comparison model. And what is comparison model? It's taking two numbers, xi and xj, and asking if xi minus xj is less than 0, equals 0, greater than 0. So it's actually hyperplanes with at most two non-zero coefficients. So this is a natural generalization of that. So how can you achieve the n to the half r using a linear decision tree? So this is probably an algorithm that you all know. So we have our input, n numbers, and we want to ask if any r of them sum up to 0. Okay? So here's a fast way to do that, non-trivial way to do that. You take all possibilities of sums of r over 2 inputs, r over 2 x's. That's n to the r over 2 choices, roughly. You compute all these sums, and then you sort them in a long list of size n to the r over 2. Okay? Then you take this list and you reverse it. So you look at all sums of minus r over 2 elements. Okay? So you take the same list and you copy it into list B, but in the reverse order. Okay? And then you take these two sorted lists, A and B, and you merge them. I'm sorry, B is taking A, reversing it, and adding a minus in front of every. Then you take these two lists and you merge them. So if you find duplicates in this merged list, and you have to take care to make sure that the coefficients that you use for the one from A do not have any coefficient in common with the one from B, but that's just technical. But if you do that, you can easily find, if you find a duplicate, then it means that basically the input is degenerate. So the complexity of what I just described is n to the r over 2 log n. And even though I did not describe it as a linear decision tree, this algorithm is in fact can be implemented as a linear decision tree. And then it's very easy to notice that all the hyperplanes that are queried by this algorithm have at most r non-zero coefficients, because we at most compare someone from the list A, which has r over 2 coefficients, with someone from the list B, which has r over 2 coefficients. Okay? So I'll just mention that the log n can be, we can get rid of it, but then this will not be any longer a uniform algorithm. So we have two improvements of Erickson's interesting result. So first of all, Erickson did not care about the dependence of the complexity as a function of r. Okay, so he considered r as a constant. And in fact, if you unfold his analysis, then you see that in fact the lower bound is n times r to the minus r, all that to the half r. Okay, so the first improvement is showing that instead of r to the minus r, you can replace it with an inverse polynomial in r. And again, this all assumes that s equals r. So what does this give us? So for example, if we no longer assume that r is fixed, so r is now a function of n, say some polynomial in n, then the old result just gives a sublinear lower bound, which is trivial. And the new result still gives something that is superlinear in n. Okay? And the tools that we use to achieve that are error correcting codes, and I'll elaborate on that in a few minutes. The second result are extending the requirement of s equals r to slightly more general requirements. One is s equals r plus 1, and it's a very modest generalization, but it was considered a major open problem. And also s equals r plus c, where c is some constant. So it's a constant compared to r. Okay? So let's see what the results. So we had for s equals r, n times inverse polynomial in r to the r over 2. For r plus 1, we have this 1 minus epsilon r here. So epsilon r tends to 0 as r grows. Okay, so this result is interesting only when r is, I think, at least 6 or something like that. But, so basically what it means is that if you add this extra coefficient that you allow the algorithm to use, then essentially you cannot do better than what you could do with r non-zero coefficients. Okay, so people ask, can you do better than the algorithm that I described by adding one non-zero coefficient? It's a natural question to ask. And it wasn't known whether you can do that or you still have the same lower bound. And it turns out that it doesn't really help you. So we tried to generalize this to c greater than 1. And unfortunately, our techniques seem to decay quite fast. So you have the same thing as before, only instead of dividing by 2, you divide by c prime, where c prime is linear in c. It's something like half c. So this means that the result decays quite fast as c increases. Okay, so this will be the major open problem that I would like to interest you in. So how to generalize the tight result of r plus 1 to r plus c. So this is the path I'll take. I'll start by proving Erickson's result for the case s equals r with the improved dependence on r that I mentioned a minute ago. So the way I'll describe it will be, I'll try to make it geometric and visual. I'll try to make it visualized. So in fact, in the paper by Erickson, the proof is very algebraic and it's quite hard to visualize it. And I think one of the main steps in this work is to show a visualization of this result. And I think this is what made it possible to break the s equals r barrier. So I'll start with that. And I'm going to skip many technical details because I want to start describing 2 and 3, which will give rise to a new linear algebraic problem which has interest in its own right. And it won't require actually 1. So like I said, the linear decision tree is a tree of hyperplanes, or queries. Okay? Denote by script q the set of query hyperplanes that are used by the tree. So each query is a hyperplane, say here n equals 2. So each query is a line in the plane. And we denote by script a of script q the induced arrangement. So I'll just say in a few words what an arrangement is. So if you have a collection of hyperplanes in space, then this creates a decomposition of space into faces. To faces. So what kind of faces do we have? So we have vertices. These are the degree 0 faces. So it's these dots here. We have the degree 1 faces, which are called edges here. So these are, say, E1 and E5. And then there are the n-dimensional faces, which are called cells. So those are the white areas. Okay. So every collection of hyperplanes induces an arrangement like this. So let's denote by script C the collection of all canonical degenerate hyperplanes. So what is a canonical hyperplane? It's a hyperplane of the form that we're trying to test. Okay, it's xi1 plus and so on plus xir equals 0 for all choices of i1 through ir. And like I said, with script Q, we denote the set of hyperplanes that are used by the algorithm that we assume the size rLDT. So a very simple observation, this was done in the late 80s, is that lower bound for deciding rLDT in the linear decision tree is log of the number of cells of the arrangement induced by C. And the reason for this is that each cell is a connected component and it's disconnected from the other cell. And every hyperplane actually divides the cells into those that are above and those that are below it and those that it crosses. Okay, so the reason you get log is information theoretic. It's for the same reason that in order to find a counterfeit coin that is lighter from other coins, you need log n ways of the set of coins. So by counting the number of cells of AC, you get a lower bound of n log n, which is much weaker than what we're looking for. So this is a technique that was known in the late 80s. And the alternative idea that we're going to use is to find in the arrangement one cell that has high complexity in some sense. Okay? So we're not going to count the number of cells, but we're going to find one that is extremely complicated and for which an algorithm that uses only r non-zero coefficient will have a very hard time to actually look at this cell. So the way I'll describe it is like a game between an adversary, which is responsible for getting the strongest lower bound, and the tree, the algorithm that we're trying to use to solve rLDT. So the game the first move is the adversary. So the adversary started with a bag of hyperplanes, which we call the canonical hyperplanes, the degenerate hyperplanes. And what it's going to do, it's going to choose a subset, which I call the critical hyperplanes, and I denote by H. So it seems like it doesn't seem like a very clever move at first. I mean, what the adversary is going to do is he's going to say, I'm going to consider only a subset, a strict subset of the canonical hyperplanes in this problem, meaning that he is guaranteeing that either the input does not lie in any hyperplane, or it lies on one of these hyperplanes, which is a strict subset. So in some sense, he's making our life easier. Okay? But we'll see that it's not exactly so. And I have to add that the strict subset that he chooses has an intersection of dimension greater than 0. Okay? So the intersection of these hyperplanes is more than just a point. And now the algorithm has a set of hyperplanes, script Q, and we consider three types of hyperplanes that the algorithm can have. It can have hyperplanes like Q1 that contain the intersection, meaning that the normal of this hyperplane is spanned by the normals of the critical hyperplanes, in other words. That's a dual way of saying that. There are hyperplanes that intersect the intersection of the critical hyperplanes in a lower dimensional subspace, a point in this case. And then, like Q2, there are hyperplanes that completely miss the intersection of the critical hyperplane. Okay, so that was the algorithm move. Now it's the adversary's move again. And what the adversary does, he finds a point on the intersection of hyperplanes and a small radius rho around this point, such that the ball of radius rho around this center, C0, misses, in this case, hyperplanes Q2 and Q3. Okay, so it misses all the hyperplanes that do not contain the intersection of the critical hyperplane. And this is always possible because the set of hyperplanes used by the algorithm is finite. And a collection of lower dimension, a finite collection of lower dimensional subspaces is never dense in Euclidean space. So you can always find a ball that misses all of them. Okay, so after the adversary does that, what's going to happen, all the action from now on is going to take place around this ball. So all the hard cases, all the hard inputs that the adversary is going to find are going to be contained in this ball. And therefore, all the hyperplanes like Q2 and Q3 are irrelevant because they cannot distinguish between anything that happens, any two things that happen in that ball. So after the adversary does this, Q2 and Q3 disappear, and the algorithm remains with a subset, which I called K, of relevant hyperplanes. Okay, and what do these hyperplanes have in common? Have in common that they contain the intersection of the critical hyperplanes that the adversary chose. So what the adversary did is force linear constraints on the hyperplanes that are relevant. Okay? All the other hyperplanes that are used by the algorithm can be thrown away. Okay, so what are the linear constraints that the adversary is going to choose? So this is his main weapon. So the first, so of course, every linear constraint that he chooses, the critical hyperplanes also have to satisfy it. Okay, so the more linear constraints he chooses, on one hand, he restricts the algorithm, but he also restricts himself because the set of critical hyperplanes is smaller. So he has to choose them in a clever way. So the first constraint that he chooses is saying that if H is a hyperplane in the set of critical hyperplanes that he chooses, then the normal, which I denote by H star, has this form. So the normal is a vector in n-dimensional space, which I write as a matrix with r rows and n divided by r columns. Okay? So the normal will have, so it's supposed to have n minus r0s and exactly r1s because it's a canonical hyperplane. So it's going to have exactly 1, 1 in every row and 0 everywhere else. And the linear constraint that it actually, equivalent way of saying this is by saying that if you take, okay, so what is the linear constraint that is forced on hyperplanes that are used by the algorithm? Hyperplanes in K, which is the relevant subset of Q. So if you write the normal to these hyperplanes in matrix form, and you multiply it by column 1 vector, you get a constant column vector. Okay, so the sum of all entries in every 2 rows is equal. Okay, so that's the first constraint. And the price of the adversary is that the size of the set of critical hyperplanes now shrinks. Instead of being n choose r, it's now n over r to the r. So it's a bit smaller. Okay, I'll show later that the size of the set of critical hyperplanes is the lower bound that we're looking for. Okay. Okay, so what can the algorithm do now? So we know that every hyperplane that is used by the algorithm has the property that the sum of the elements of every 2 rows is equal. So it has 2 types of weapon, which I call A and B. So I decompose K into Ka and Kb. What is Ka? K consists of queries such that the normal, which I denote by Q star, has at least 1 null row. Okay, at least one of the row is full of zeros. One of the rows is full of zeros. And the second is queries such that no row is full of zeros. So every row has at least 1 non-zero. But since we're assuming the model where the number of non-zero coefficients equals r at most, and we have r rows, it means that every row has to have exactly 1 non-zero coefficient. Right? We don't have enough coefficients for any row to have more than that. And since the sum of every 2 rows is equal, we can assume that these coefficients equal 1. Okay, so we have these 2 types of queries that can be used by the algorithm. So the first case, which is the hard case, like I said, is the case where case of queries in the subset of relevant hyperplanes that have a null row. But we know that since the sum of every two rows is equal, it means that the sum of any row equals 0, because we have at least one 0 row. So it means that every non-null row has to have at least two non-zeros, because in order if you want to have a sum of non-zeros that equals 0, you have to have at least two of them. Okay, but we have at most r non-zero coefficients. So the best we can do is pair the non-zero coefficient 2 in a row. So this means that there are at most r over 2 floor non-null rows, meaning that in fact if one row is null, then half the rows are null. Okay? And now what does the adversary do? So the adversary what he can do, he can force more linear constraints. So we know from the theory of error-correcting codes, actually over a finite field, but this is just a small problem, that there exist big subspaces of linear spaces over finite fields that have the property that no vector except the 0 vector in this subspace has too many zeros. Okay, this is called an error-correcting code. And I won't go into the technical details of what the adversary does, but this is the linear constraint that he imposes. So if you take the normal to the query, multiply it by this vector, the vector of 1 to m, then the result belongs to the span of a linear error-correcting codes. So this error-correcting code is built using standard tools. Just say what the details are. So it's an error-correcting code over fp for some prime p of dimension r, and the distance of the error-correcting code is at least half r, meaning that every vector in this error-correcting code has at least r over 2 non-zeros, unless it's the 0 vector. And what the adversary gains from this is that since the vector q has so many null rows, has so many zeros, that if you multiply it by this parity checking vector, you get 0. Okay? And the price that it pays is, I won't show exactly the calculation, but instead of having n to the r possible critical hyperplanes, so I repeat, the critical hyperplanes also have to satisfy this constraint. I mean, the hyperplanes that the adversary keeps in his bag also have to satisfy the same constraint. So the number of such hyperplanes, a simple calculation shows, is n times this r to the minus 3, and instead of to the r, we have to the half r. Okay, so the adversary has a very small number of degrees of freedom. In fact, instead of being able to choose a vector with an arbitrary position of 1 in every row, the adversary can only choose an arbitrary position of 1s in the first half rows, and the bottom half rows will be the error-correcting code of that. So they'll be determined by that choice. So that's why it's only to the half r and not to the r. And the second case of the relevant queries of the algorithm is queries that have no null row. So they just look like this. Okay? And so let's see again what happens. We had a game between the adversary and the algorithm, and the adversary chose a subset of the set of critical hyperplanes, of degenerate hyperplanes, that have this high dependence, that have all this sum of two rows equal, and we have the error-correcting code constraint. And the algorithm now has only a subset k of relevant hyperplanes that it can use, and there are two types, ka with the null row and kb. And these hyperplanes have a very constrained structure. So what is the main technical lemma? So if you look at the arrangement that is induced by the set of relevant hyperplanes that are used by the algorithm, it has a complex face that we call f. So what I mean by complex face? So it has the following property. First of all, it's non-degenerate. Okay, so every point in the space does not lie in any canonical hyperplane. All the hyperplanes, all the critical hyperplanes that are in the adversary's bag are tangent to the space F. And for any such hyperplane that it is tangent, you can pick a tangent point pH, which I call the collapse point, such that no two such points can be simultaneously separated from the interior by a hyperplane that is used by the algorithm. Okay, so here's a drawing. So this is the face F, and it's non-degenerate, meaning that if the input is this red point, then the answer of the algorithm has to be no. Okay, and these are the collapse point corresponding to the critical hyperplanes, pH1, pH2, and pH3. And they are degenerate because they belong to the critical hyperplanes. And the main technical lemma is that using the hyperplanes in Ka union Kb, it is not possible to distinguish simultaneously between two of these points, pH2 and pH3, say, and the laser point. Distinguish, I mean, pass a hyperplane where one point is on one side and one point is on the other side, or one is on the hyperplane and one is not on the hyperplane. Okay, so what this means is that the depth of the tree is at least the cardinality of the set of critical hyperplanes. Okay, because at every move you can distinguish at most between one point on this bound, one tangent point, and the laser point. Okay, so if you follow the path of the tree on the laser point, and its length is less than the cardinality of a set of critical hyperplanes, then it means that one of the points on the boundary, one of the collapse point, was not distinguished with the laser point. So it means that if the adversary now moves the laser point to that collapse point that was not tested for, then the algorithm cannot feel the difference. It will output the same answer, but these 2 points have different answers, so it cannot decide. So it's very technical to show why all these linear constraints that I showed on Ka and Kb have this face, which has this very vital property. Well, it's in the paper, but the main idea I wanted to show is that the adversary creates these linear constraints, and then you can use structural property of the hyperplanes that satisfy these constraints to get this this geometrically complicated face. And I'll move to the case S equals r plus 1, which is the case that we extended. So what happens if S equals r plus 1? So the algorithm now has a new tool. It can ask queries with a normal that looks like this. So what happens now, we have in every row there's exactly 1, 1, and everything else is 0. But there's one row that has 2 non-zeros, A and B. So we have r plus 1 non-zero coefficients. And this is a query that the algorithm can use. So we know that the sum of A and B is 1 because the sum of every 2 rows has to be equal. But the problem is that the main technical lemma, which I just described, no longer works. So in fact, using these queries, these new weapons, it's possible to distinguish between more than one point, one collapse point, and the interior. So the main technical lemma no longer works, and that's where Erickson's work was stuck. So what does the adversary do with these queries? And the answer is that it's going to impose some new linear constraints. So these new linear constraints will force this hyperplane not to be relevant anymore. So it will not be in K. So how is it going to enforce these constraints without shrinking too much the size of the set of critical hyperplanes, which is the lower bound? Okay, so this gives rise to the following combinatorial linear algebraic question, which can be described regardless of everything I talked about. So we define good matrices of size r by m as matrices that have exactly one non-zero coefficient in every row, and this coefficient is equal, so we can assume it's 1. Okay, so this is the set of good matrices of size r by m. A bad matrix, B, is a matrix of the same size that has one extraneous coefficient. So here are two examples. So in this example, we have the extraneous coefficient in this row because it has two non-zeros, and they sum up to 1. And in this case, we have coefficients -2 and 3 that sum up to 1. So you see that every row has exactly 1, 1, except for one row that is violating that. It has two non-zeros that sum up to 1. So the question is, what is the maximal subset of the set of good matrices, the span of which does not intersect this set of bad matrices? Okay, and why do we want this set to be big? Because a bigger subspace means less linear constraints that the adversary would have to suffer as well. Okay, so what is the maximal subset such that its span does not have any bad matrix? And we denote by FRM the maximal size of such G prime. Maximal size of a set of R by M matrices, R by M good matrices, the span of which does not have a bad matrix. So here's, we start with a good lower bound for FRR, for square matrices. So permutation matrices, size R by R, are matrices that have exactly one in every row and in every column. Okay, so the first lemma that we prove is that the span of permutation matrices of size R does not contain any bad matrix. Okay, so in particular, it means that FRR is at least R factorial. That's the number of permutation matrices. And we do not know if this is 10. So what happens when we want an arbitrary number of columns? So let's start with a number of columns that equals r to the k for some integer k. So now we'll look at matrices with r rows and r to the k columns. So first we need to define some notion of a tensor product of matrices. So this is actually a half tensor product. So for two matrices, one with M1 columns, one with M2 columns, we define the tensor product as a matrix with the product number of columns. And I'll just define it using an example, using permutation matrices, which is the only example we really need. So we have two 3x3 matrices, and we get a 3x9 matrix. So the columns in the first matrix index the columns inside every block, and the columns in the second matrix index the block. So for example, here we have a 1 in block 1 and in column 2 inside block 1, so we have a 1 here. Here we have block 3 and column 1 inside block 3, so we have a 1 here. So on. Okay, so it's formally defined like this, but it's best to see it with an example. Okay, so it's actually a tensor product only in the columns in some sense. And for a subset of square matrices, we denote the k-fold tensor product of the set with itself as all possibilities of taking k vectors from the set and computing the tensor product of these k vectors. Okay, so we have x1, tensor x2, tensor so on, tensor xk, where x1 through xk are all from x. Okay, so that's a k-fold tensor product of a set of matrices. And these are matrices of size r by r to the k, which is exactly what we need. So the second main lemma is that in order to get a lower bound for fr r to the k, it's enough to look at the k-fold tensor product of permutation matrices of size r. So these are exactly matrices of size r by r to the k. And it turns out that the span of these matrices does not contain any bad matrix of the corresponding size. Okay, so the conclusion is that f r to the k is at least r factorial all that to the k. Actually, there's a technical detail I'm not saying, but basically that. And if we want some general m, what we can do is just take the largest k that fits inside m. So frm is at least r factorial, all that to the log m over log r. And now we need to apply this lower bound for f to the problem of rLDT, lower bounding rLDT. So we approximate the factorial using Stirling's formula and so on. And this is where we get the 1 minus epsilon r that I talked about earlier in the new lower bound for r plus 1. Okay, so because of the choice of permutation matrices is not just any matrix, tensor products of permutation matrices is not just any matrix, we get a small payment that we get here. So epsilon r is something like 1 over log r, something like that. Okay. So,
just out of curiosity, what happens when you take random? Just randomly just choose these elements. How big can you get?
Random good matrices to see when you hit the first band. We haven't computed that. We haven't considered that. So, so this approach might solve the s greater than r plus 1. But so why intuitively why would it be? Okay. It's an interesting approach. I have. So what happens if s is greater than r plus 1? So now the algorithm threatens to use matrices with more rows with more non-zeros, right? So the adversary needs more linear constraints that will make these queries irrelevant. Right? Take them out of K. So here's a quick and dirty way to do it, which is by no means optimal. At least I don't believe it's optimal. So you subdivide the R rows to blocks, to a number of blocks. And the linear constraint is going to be that every 2 blocks are equal. OK? And then within each block, we're going to force the permutation of tensor products, the tensor product of permutation construction, which is, by the way, a linear constraint, but I did not mention it. OK? So this is supposed to be H star. I apologize for that. So this is what the normals to the queries are going to look like. Identical blocks A, one on top of the other. So this time, the adversary pays a high price, but the question is, OK, let me just explain why this solves the case of S equals R plus C for some constant C. So the idea is that if the algorithm wants to use many non-zero coefficients, many extra non-zero coefficients in many rows, then it's going to have to copy it many times. Because say if the algorithm has 2 non-zeros, 2 extra non-zeros in block A, then it's going to be copied lambda times, where lambda is chosen carefully. So if you choose lambda such that lambda times, say, 2 non-zero coefficients in 2 rows is greater than what the algorithm can use, then the algorithm will not be able to use it. Okay? That's the main idea, and it's kind of quick and dirty, and it gives a very low, a very poor bound when, if you consider S equals R plus C, where C is, I don't know, 5 or something. So that's the idea of the construction, and it's probably not optimal. And this is the main problem that we've been thinking of after this work came out. So what is there a tight construction that gives something of the spirit of the result of S equals R plus 1 and S equals R, or R plus C? So we tried to somehow, one idea we tried was to generalize the permutations to, say, Latin squares or some higher high-order combinatorial structures, and nothing seemed to work. So maybe this idea that Asaf mentioned, that'd be an interesting approach. So finish with some conclusions. So first of all, I described the notorious open problem of 3-sum. And like I said, because of the price of 1 minus epsilon r that we pay in the exponent of the lower bound, it turns out that actually r has to be at least 5 or 6, something like that, in order for this result to be non-trivial. Okay, so r equals 3 is somehow left out, and it would be nice to see if something can be done there using maybe similar techniques. The main question is whether our quick and dirty construction for s greater than r plus 1 is tight, which I believe is not. And then if you remember earlier, I said that Mayer-Ofterheide said that if you assume just any linear decision tree with as many non-zero coefficients as you want, then you get an upper bound of n to the 4th log n maybe, which does not even depend on r. So it seems like somewhere between s equals r and s maximum, which is s equals n, there's a giant unexplored territory. So this is just actually a tip of an iceberg. So what happens, say, if you assume s equals constant times r, for example? So where does it break down and become more like Mayer-Ofterheide's result when you move the knob of s up? And then there are results mainly by some by Andrew Yao, some by other people, Bjorner, of using topological techniques for solving the same problem. And in one paper, for example, they show how using how by counting the Betty numbers of the arrangements that are induced by the set of canonical hyperplanes, but for a different problem, they show how to get different types of lower bounds. These results seem to generalize the bound that I described earlier of log of the number of connected components of the arrangement. But it would be nice to see if some generalization of those results can be somehow maybe used together with this type of result. And of course, there's the so the problem of good matrices and bad matrices. I think it falls into the same framework of the more general field of error correcting codes, where we want to find big subspaces that somehow avoid certain vectors that have combinatorial constraints. Okay, so this is what an error correcting code does. It's a big subspace that avoids vectors that have too many zeros, which is a combinatorial property. So I think these problems are very interesting. Also, there's been some work on randomized linear decision trees, and we haven't thought of using those together with these techniques. There's an interesting problem someone proposed of approximate degeneracy, where instead of asking if the sum of r coordinates equals 0, you ask if it's small, say at most some epsilon, and of course you have to assume some normalization. And I think these results should apply to that somehow, but I haven't yet really dived into that. And of course, there's a natural question of asking about higher order degeneracy testing, namely of polynomials of higher degree higher than 1, which is what we consider. And I guess that's it.
So I guess it seems like the hardest value of r would be like n over 2. If r is very close to n, then I guess it becomes easy again.
Well, a trivial algorithm is n choose r, so if r is too big, then...
Right. But then I guess my question is...
The number of hyperplanes is maximized when r equals n over 2, so that'd be a good input.
But there's no lower bound for this case right now?
Not that I know of.